value of the method that the func delegate encapsulates. The out keyword in this context means that the return type is covariant. The action generic delegates allow a developer to encapsulate a method that can have 0 to 16 parameters and must not return a value. The predicate generic delegate encapsulates a method that contains one parameter and returns a value that must be of the Boolean data type. A predicate delegate represents a method that defines a set of criteria and determines whether the specified object meets those criteria. Let's look at code examples using each of the built-in generic delegates, i.e. func, action, and predicate. At the end of the tutorial, we'll look at an example of using an extension method that takes a predicate as an argument. Let's start by looking at an example using the func built-in generic delegate. Let's create a .NET Core Console project. I'll name this project and solution func action predicate examples. Let's create a public class named math class and add one method named sum. The sum method contains two parameters of the int data type and returns a value of the int data type. This method simply returns the integer result of the sum of two integer arguments passed into this method. Let's instantiate the math class in the main method. Let's use the generic built-in func delegate to encapsulate the sum method. All type parameters passed into the func delegate are of the int data type. The last type parameter represents the return type, and the first two type parameters represent the method's parameters data types. So as you can see, through the use of generics, we have made our func delegate compatible with the sum instance method. We have strongly typed the func delegate with the int data type for the parameter types and the return type. We can therefore use the func delegate to encapsulate the sum method. Let's write code to execute the delegate and then code to write the result to the screen. Let's test the code. Great! We can replace the sum method with an anonymous method using the delegate keyword like this. An anonymous method is, as the name suggests, a method that does not have a name. Let's test the code. Great! We can further abstract the method by removing the delegate keyword, the return keyword, the curly brackets, and the parameter type definitions. So here we have now reduced the functionality of the sum method to a lambda expression. A lambda expression is an anonymous function which, as discussed, is a defined function not bound to an identifier. We previously created the same function using the delegate keyword. A lambda expression is a shorter way of representing an anonymous method. Lambda expressions were introduced in C# version 3 along with LINQ. For more information on LINQ, please navigate to this URL. Let's test our code. Excellent. To further understand the func generic built-in delegates, let's create our own imitations of a few of the built-in func delegates. Let's call our delegates func2. And we can now replace the func keyword with func2 in our code. Great! But we don't need to do this because appropriate generic delegates are already available to us in the system namespace. Let's create a slightly more complex example where our delegate encapsulates a lambda expression that performs the functionality of adding two operands of the float data type together, then multiplies the result of this operation by a value that is of the int data type. Great! Let's create a more practical example where our lambda expression adds a bonus to an employee's annual salary. Great! So let's look at some examples using the action generic built-in delegate. So in this example, let's create a lambda expression that accepts fields for an employee record as arguments and outputs the employee details to the console screen. Note that the action delegate is used to encapsulate a method that does not return a value. So in this example, we'll output three fields of an employee record to the console screen: ID, first name, and last name. Great! Let's add an annual salary field. So to do this, we can use a different action delegate to accommodate this new field. Let's update the lambda expression accordingly. Let's add a gender field, which is of the char data type, and a Boolean field representing whether an employee is a manager or not a manager. So to achieve this, we need to use a different action delegate that can accommodate the two new fields. Excellent. So let's use an example where we'll use the predicate built-in generic delegate. Let's first create an employee class. Let's create a generic list that will contain 4 objects of the employee data type. Let's add some employee objects that contain made-up employee details to the employees list. Now let's create a method that will filter the employees list based on criteria that will be passed to the method in the form of a predicate. So this method simply traverses the employees list. If employee items within the list meet the criteria of the predicate passed into the method, the relevant item is added to another list that is returned to the calling code once all the items in the original list passed into this method have been traversed and evaluated. So let's call the filter employees method and pass in the employees list followed by the Lambda expression, which is encapsulated by a predicate delegate. Let's say our Lambda expression in this example is used to return only male employees. Let's write code to traverse the list returned by the filter employees method and use the display employee records action delegate, which I have now renamed to display employee details just for better readability, that we created in the previous example to write the relevant employee records to the console screen. Let's test the code. Great! Let's alter the logic of our predicate so that we return only details for employees that earn less than $45,000 a year. Great! Let's alter our logic so that we only return employee details for employees that are managers. Great! So we can abstract this code even further through the use of an extension method. So let's create a public static class named extensions. Let's copy the filter employees method to our extensions static class. Let's make the filter employees method public, and it must also be static. Then to finish making this method an extension method, all we need to do is add the this keyword before the first parameter. The first parameter is defined as a generic list that is strongly typed with the employee user-defined type. So the filter employee extension method should now automatically be available on generic lists that are strongly typed with the employee user-defined type in our main method. If you are not clear on extension methods, don't worry, extension methods will be discussed in detail in upcoming tutorials. Basically, through extension methods, the developer can add methods to existing types without creating a new derived type, recompiling, or modifying the original type. So let's see if we can access the filter employees method on the employees generic list. And there it is. It shows up in the IntelliSense as expected. So we no longer need to pass the employees list to the filter employees method as a parameter, and all we need to do is pass in the Lambda expression. Let's test the code. Great! The system.link namespace contains a number of extension methods. Let's demonstrate how we can use an extension method which is available in the system.link namespace to achieve the same result. Link is beyond the scope of this tutorial. We'll look at link in detail in upcoming videos. Let's include a directive to the system.link namespace at the top of our code. The where extension method is available on the generic IEnumerable type. The generic list type implements the IEnumerable generic interface. So now that we have added the system.link directive, the where extension method should now be available on the employees list object. So let's replace the filter employees method with the where method. The where method returns a value of type IEnumerable, so we must convert our result to a generic list using the toList explicit conversion method. Let's test the code. Great! So let's finish up by using the func delegate that we created earlier to add a bonus to the employee annual salary fields of each of our employee objects stored in the employees list. Let's test the code. Excellent! I hope you have enjoyed this tutorial on the three built-in generic delegates, namely func, action, and predicate. Hi and welcome. This is the fifth part of a video series on delegates. This is also the final part of this video series on delegates, but there are a lot more upcoming videos to be released as part of this advanced C# course. In this video, we'll look at how delegates can be used to encapsulate a callback method. So, what is a callback method? Basically, callbacks are simple functions which are used to notify the calling instance when an asynchronous code block has been executed and the result is available. So I found a great code example on a Microsoft Docs webpage that uses a callback method encapsulated by a delegate to run code when asynchronous tasks have completed. The code in this code sample performs a basic function of retrieving the IP addresses associated with user-inputted domain names using the .NET built-in DNS static class. For example, if we input Microsoft.com, the DNS class, behind the scenes as it were, asynchronously looks up the IP addresses associated with the Microsoft.com domain name. I'm going to simply copy this sample code demonstrating the use of a callback method into a .NET Core console application. We can then demonstrate the code and go through the code step by step to understand how it works. Basically, this code demonstrates using asynchronous methods available in the built-in DNS static class to retrieve domain name system information for user-specified domain names. You can navigate to this URL to copy the relevant sample code as well as read more information about the sample code. A link to this URL has also been included below in the description. So let's create a .NET Core console application. Let's name this project and solution DNS Async Callback Sample Code. Let's copy the code from the relevant web page and paste it into the project we have just created. So to do this, we can select all the code that has been auto-generated in our program.cs class file and paste the code currently copied to our clipboards over the selected code. Right, so let's start by running the code. So let's enter a few well-known domain names. This code has been written so that we can press the Enter key without entering anything at the input prompt as an indication that we are finished inputting our data. So let's enter a few domain names. So for the first entry, let's enter google.com. For the second entry, let's enter microsoft.com. And for the third entry, let's enter yahoo.com. Right, let's press the Enter key without entering anything at the command prompt to indicate that we are finished inputting our data. And in the output presented to the screen, we can see three headings, namely addresses for Google, addresses for Microsoft, and addresses for Yahoo. Under these headings are the IP addresses relevant to the domain names that we have entered. If you're interested in reading more about what DNS, i.e. Domain Name System is, please navigate to this URL. So let's go through the code to see how a delegate is used to encapsulate a method that is used as a callback method through the execution of the relevant delegate once relevant asynchronous tasks have been completed. So the first line of code in the main method instantiates a delegate named async callback. This delegate is built into .NET and is provided specifically for the purpose of encapsulating callback methods that are used during asynchronous operations. So I'm going to right-click the delegate name in the Visual Studio Code Editor and click the context menu item named Go to Definition. And here we are presented with the delegate definition of the async callback delegate. This delegate can encapsulate a method that doesn't return a value and contains one parameter of the iAsync result type. And if we look at the iAsync result type, this interface provides a standard definition for objects that are passed as an argument to the callback method. The relevant object that implements the iAsync result interface represents the status of an asynchronous operation. You can see here the async state read-only property gets a user-defined object that qualifies or contains information about an asynchronous operation. Okay, so let's go back to our code, and you'll see that a method name is passed into the constructor of the async callback delegate in the code written for the purpose of instantiating an object derived from the async callback delegate type. So our callback method is named processDNSInformation. Let's have a brief look at this method. You can see its method signature conforms to the method definition defined in the async callback delegate. So we'll come back to this method in a bit. For now, let's go back to the code in the main method. So next, the code is prompting the user for domain names. And you can see that for each entry, the DNS.BeginGetHostEntry method is fired. DNS is a static class provided in .NET and provides simple domain name resolution functionality. The DNS.BeginGetHostEntry method asynchronously returns the Internet Protocol IP addresses for the specified host. You can see that our delegate named callback that encapsulates our callback method named processDNSInformation is passed as an argument to the DNS.BeginGetHostEntry method. Here the code essentially informs the DNS static class of the memory address of our designated callback method, which is stored in the callback delegate object. Note that above this line of code, we have a line of code that increments an integer variable named requestCounter. The number of asynchronous tasks is stored in the integer variable. Now, the reason why this incrementation is done in an unusual way here, whereby the .NET built-in interlocked.increment method is used for this purpose, is because each time our asynchronous process is kicked off, as it were, by the DNS.BeginGetHostEntry method, a new thread is created and executed in parallel, asynchronously, to the main thread. When each asynchronous process is finished processing, the callback method is executed on the main thread, and if we go back to our callback method, you can see that each time an asynchronous task completes, the request counter variable's value is decremented within the processDNSInformation callback method. So, because the timing of when this callback method will be called by potentially multiple threads is uncertain, we must ensure that the request counter variable is updated in a thread-safe way. Multi-threading solves problems with throughput and responsiveness, but in doing so, it introduces new problems, deadlocks, and race conditions. For more information in this regard, please navigate to this URL. So the next line of code monitors the state of the value of the request counter variable. When the request counter variable's value is 0, we know that all asynchronous tasks have completed, which means our output data is ready to be presented to the screen. So this while loop ensures that if our asynchronous tasks have not yet completed, that the subsequent lines of code responsible for outputting the results of the asynchronous tasks are only executed once the asynchronous tasks have completed. So this while loop will continue processing and outputting status information to the screen until the request counter variable has been decremented to 0 within the callback method, i.e. the processDNSInformation method. So let's look at the processDNSInformation callback method. And you can see the DNS.endGetHostEntry method is called to return the result of an asynchronous task. The DNS.BeginGetHostEntry method and the DNS.endGetHostEntry method are used for asynchronous processing. The DNS.endGetHostEntry method gets called from within the callback method. Remember, a reference to the callback method was passed as an argument to the DNS.BeginGetHostEntry method. This was done by passing the async callback delegate object stored in a variable named callback to the DNS.BeginGetHostEntry method as an argument. Remember, an async callback delegate object was coded to encapsulate the process DNS information method within the main method. This object was then passed as an argument to the DNS.BeginGetHostEntry method. So the application knows that an asynchronous task has completed because at this stage the callback method, process DNS information method, has been invoked. So within the callback method, it is safe to call the DNS.EndGetHostEntry method to return the result of the asynchronous task to the calling code. So the results here are stored in an array list member variable named host data. The host data array list can be used to retrieve the relevant results and present the relevant results to the console screen. And you can see the code here in the main method responsible for outputting the results of each asynchronous task to the console screen. So the IP addresses relevant to the domain names entered by the user are written to the console screen. Let's run the code and enter some domain names. Excellent. Note that the code we have just demonstrated here uses the asynchronous programming model APM pattern, also called the iAsync result pattern, which is the legacy model that uses the iAsync result interface to provide asynchronous behavior. Microsoft recommends, moving forward, that we use the task-based asynchronous pattern, TAP, for asynchronous programming, which uses a single method to represent the initiation and completion of an asynchronous operation. The async and await keywords in C# add language support for the task-based asynchronous pattern. We'll look at the task-based asynchronous pattern, TAP, in detail in upcoming tutorials. This video serves as a demonstration of how delegates can be used to encapsulate callback methods and also serves as a brief introduction to asynchronous programming. We'll look at the recommended approach to asynchronous programming, i.e., the task-based asynchronous pattern, TAP, in upcoming videos. Please navigate to this URL for more information on asynchronous programming patterns available in C#. To summarize, in this 5-part video series on delegates, we discussed that a delegate is a reference type in C# that references a method that contains a particular parameter list and return type. We discussed that due to a concept called variance, the delegate definition does not have to exactly match the parameter types or the return type of the method that it encapsulates. Contravariance means that a delegate, for example, can reference a method where a particular parameter in the delegate's definition is more derived than the parameter counterpart contained within the method that it encapsulates. Covariance means that the return type in the delegate's definition can be less derived than the return type of the method that it encapsulates. We looked at 3 built-in generic delegates, namely func, action, and predicate. We looked at how these generic delegates can be used in code for better code reuse, type safety, and to improve performance. We also briefly looked at anonymous methods, lambda expressions, and extension methods. In this final video on delegates, we looked at how a delegate can be used to encapsulate a callback method that can be called once an asynchronous task is completed. We haven't looked at delegates in relation to events yet. An upcoming tutorial on events will include how delegates are used in relation to events in C#. I hope you have enjoyed this tutorial on asynchronous programming using delegates to encapsulate callback methods. And I hope you have enjoyed this video series on delegates. If you didn't fully understand all the concepts discussed in this video, please don't worry. The more you practice, the more you'll understand and the more proficient you'll become as a software engineer. Learning to become a proficient software engineer is a marathon and not a sprint. I'd also like to add that I think it is more important to understand the concepts behind the code rather than the code itself. Hi and welcome. This is the first part of a tutorial on C# events. In this video, we'll look at the basics of C# events by examining a piece of code taken from a Microsoft Docs webpage. For more content on advanced C# concepts like this and much more, please consider subscribing. And please ring the bell so that you'll be notified of future releases from this channel. I usually use my Windows PC to record my demonstrations, but I've decided to demonstrate this code example using Visual Studio 2019 Community Edition for Mac. It doesn't ultimately matter which code editor you use if you want to follow along. It makes no difference because this video is about the code, more specifically about the basics of what events are and how they relate to delegates. So I'm going to use Visual Studio 2019 for Mac Community Edition to create a .NET Core console project. You can name it what you like. I'll name this project Threshold Reached Event Application. I'm going to copy the code from the appropriate Microsoft Docs webpage and paste it over the code in the program.cs file like this. This code sample is available at this URL. So the code here performs a very basic function. It first generates a random integer value, which can be any non-zero integer value, where the maximum value is 10. This integer value serves in this example as a threshold value. The code then prompts the user to press the A key to increment an integer value by a value of 1. When the integer value has been incremented to the extent that it reaches the threshold value, i.e. the generated random integer value, an event is raised, and the calling code handles the raised event by outputting text stating that the threshold value has been reached. The text also includes the date and time when the threshold value was reached, by the value that the user is able to increment by pressing the A key. So let's start by running the code, and then we'll look at the code in order to see how an event and a delegate have been implemented in the code. Let's press the A key until the threshold is reached. And the threshold has been reached, so the event is raised and the event handler outputs appropriate text to the console screen. So what exactly is an event in C#? Events are special kinds of multicast delegates that can only be invoked from within the class or struct where they are declared. If other classes or structs subscribe to the event, their event handler methods will be called when the class where the delegate has been declared raises the event. Events can be marked as public, private, protected, internal, or private protected. These access modifiers define how users of the class can access the event. For more information on access modifiers, please navigate to this URL. Events in .NET are based on the delegate model. The delegate model follows the observer design pattern, which enables the subscriber to register with and receive notifications from a provider. We'll discuss the observer design pattern in an upcoming video. An event sender pushes a notification that an event has happened, and an event receiver receives the notification and defines a response to it. An event is a message sent by an object to signal the occurrence of an action. Delegates were explored in detail in the last tutorial, the third part of this course. Links to the playlist on delegates have been included below in the description. You can also access this playlist through the card available in the top right-hand corner of your screen. Let's recap. What is a delegate? A delegate is a type that holds a reference to a method. A delegate is declared with a signature that shows the return type and parameters for the method it references. And it can hold references only to methods that match its signature. A delegate is thus equivalent to a type-safe function pointer or a callback. A delegate declaration is sufficient to define a delegate class. Right, let's look at our code example to see how an event can be implemented in C#. So an event can be fired through a user action, for example, button press, or through the code logic itself. In this example, the event is raised through the code logic. Here, we have a user-defined class named counter where an event is declared. The name of the event is threshold reached. Let's look at how this event is defined. So this event has a public access modifier. And to define an event, we must use the event keyword. Then the event keyword is followed by a built-in C# delegate named event handler. Delegates have many uses in .NET. In the context of events, a delegate is an intermediary, or pointer-like mechanism, between the event source and the code that handles the event. You associate a delegate with an event by including the delegate type in the event declaration. Let's select the event handler delegate name in the code editor. Let's right-click and select the Go To Declaration menu option. If you are using Visual Studio for Windows, this context menu item will be marked Go To Definition. So here you can see the event handler delegate declaration that can be used to store a reference to a method that contains a matching parameter list and return type to the event handler's parameter list and return type in the delegate definition. This is a built-in delegate provided in the system namespace. Notice the t-event-args generic parameter. There is another built-in event handler delegate of the same name also provided in the system namespace. This particular delegate declaration looks like this. The difference between this delegate and the one we are using is you are restricted to using the event-args class to provide event data to the event handler method using this delegate. Notice that in the definition of the event handler delegate that we are using, we are able to provide a type parameter through generics. This means we are not restricted to the use of the event-args class to pass data to the event handler method, and we can use a custom class for this purpose. Here you can see we are using the threshold reached event-args custom class where data about an event can be stored in two public properties, namely threshold and time reached. So this event handler delegate contains two parameters in its delegate definition. The first parameter is of type object, which allows for the calling code event handler method to accept an argument that references an object instance derived from the class where the relevant event resides. The this keyword can be used as a reference to the object that contains the event. So the this keyword can be used to pass a reference of the sender object to the appropriate event handler method when the relevant event is raised. The second parameter through generics allows a developer to define a type for this parameter. The advantage of being able to use generics with this delegate is that we are able to create our own custom user-defined type that can contain the relevant event data, which can be passed as an argument to an appropriate event handler method in the calling code. So let's look at a basic overview of the counter class, i.e. the user-defined type where our event is declared. Here we have two member variables, both of the integer date type. One to store the threshold value, the other to store a value that will be incremented by the user. So the threshold value is passed through by the calling code through a parameterized constructor when the calling code instantiates an object derived from the counter class. The passed-in argument is then stored in the member variable named threshold. Let's look at the add method. This method can be used to increment the member variable named total. The value stored in the total member variable is then compared to the value stored in the threshold member variable. If the value stored in the total variable, which is incremented by the user, reaches the value stored in the threshold variable, an event is raised. Let's look at the code responsible for raising the relevant event. Firstly, an object derived from the threshold reached event args class is instantiated. The threshold reached event args user-defined type is the custom type we have passed as a parameter to the event handler delegate. An object instantiated from the threshold reached event args class can be used to store event information. If you look at the threshold reached event args class, you can see that it contains two properties, one named threshold for storing the threshold value, and the other named time reached when the user incremented value stored in the total member variable reached the value stored in the threshold member variable. So these two properties are appropriately set on an object derived from the threshold reached event args class. This object is then passed into a method named onThresholdReached. The onThresholdReached method contains the logic for raising the appropriate event. In this method, code is first created where a variable named handler is used for referencing the threshold reached event. The next line of code is an if statement checking if the handler variable contains a value. If the handler variable is null, this means that calling code has not subscribed to the relevant event, which means no appropriate method has been designated on the client calling code to handle the relevant event when the event is raised. In a bit, we'll look at how a calling client can subscribe to an event that resides in a particular class. So, if, however, calling client code has subscribed to the relevant event, the handler delegate is invoked. This delegate will point to a method that has been defined in the calling client code. The relevant method is designated to handle the relevant event at the point where the calling client subscribes to the relevant event. So let's look at the calling client code. Let's go to the main method. So the first line of code is instantiating an object derived from the counter class. Note that the random.next method is being used to pass a non-negative random integer that is less than the specified maximum, which in this case is hard-coded to a value of 10. So the randomly generated number is our threshold, which will be stored in the relevant object derived from the counter class. So the object derived from the counter class is stored in a variable named C. Using the object referenced by the C variable, we are now able to subscribe to the event named thresholdReached, which is declared in the counter class. So the code here is assigned a method that resides in the program class to the thresholdReached event. We can do this because the method named C_thresholdReached is compatible with the event handler delegate. In other words, the parameter list and the return type of the C_thresholdReached method definition matches the parameter list and return type of the event handler delegate definition. The effect of this is that when the threshold-reached event is raised from the add method within the counter class, the subscribed method in the calling code, i.e., the C_threshold-reached method, will be invoked. A reference to the relevant object derived from the counter class or sender object is passed in to the C_threshold-reached method, as well as the object that stores the relevant event data, in this case the object derived from the threshold-reached event args class. Note how in this example the event handler delegate is an abstraction that allows any calling client that contains a method with a method definition that matches the event handler delegate definition to handle what happens when the relevant event is raised. This means the calling client is loosely coupled with the class where the event is declared. You see, the calling code doesn't have to know anything about the class where the event is declared, and the class where the event is declared doesn't need to know anything about the calling code. The event handler delegate, in this case, is used to establish a loose coupling. This is a key concept to understand when it comes to using events in C#, how delegates can be used to create a loose coupling between components. So let's watch this in action. Let's put a breakpoint in the code to a point where the value incremented by the user has reached the threshold value and the event is about to fire. We can then see what happens when the threshold reached event is raised. Let's run the code. And let's press the A key to increment the value that is compared to the threshold value until our breakpoint is hit, which means the user incremented value matches the threshold value. And there it is, our breakpoint has been hit. So, a variable named handler is set to the threshold reached event. The code checks if the handler variable is null. If the handler variable is not null, this means the calling code has subscribed to the event. So I'm going to put a break within the C_threshold reached method, which is the designated method for handling the relevant event. And when we step through the code, the threshold reached event is raised. The C_threshold reached method is invoked, and the C_threshold_reached method handles the event in the custom way that the method has been coded. And if we look at the values associated with the two arguments passed into the C_threshold_reached method, we can see that this is an expected result. We have the sender object, which is the object from where the event was raised, and we have an object derived from the threshold reached event args class, where the relevant event data is stored. And let's press F5 to run the code right through, and you can see the expected output presented to the screen. I hope you've enjoyed this video on the basics of events in C#. Please consider subscribing for more content on advanced C# concepts like this and much more. And please ring the bell so that you can be notified of future content released by this channel. If you feel you have gained value from viewing this video, please consider hitting the like button, and please feel free to share any of my videos with anyone you feel may benefit from their content. A link to the Microsoft web page that contains the code example I have used in this video is available below in the description. Hi and welcome. This video is the second part of a tutorial on events in C#. In this video, we'll create a practical example where multiple events exist in a class. We'll look at using add and remove accesses to encapsulate the functionality that gets executed when client code or calling code subscribes or unsubscribes to the relevant events. Code within the add accessor is executed when the client code subscribes to the relevant event. Code within the remove accessor is executed when the client code unsubscribes to the relevant event. We'll use the event handler list built-in C# collection class to store the relevant delegates associated with the relevant events when the calling code subscribes. The event handler list collection class is a built-in C# collection class that can be found in the system.component model namespace and is a collection specially suited for storing delegates. So here's the basic idea behind this code example. A device, could be any device, contains a thermostat which contains a heat sensor as well as a cooling mechanism. So we'll have a class to represent the device, a class to represent the heat sensor, and a class to represent the cooling mechanism. Each of these classes will implement an appropriate interface. So the heat sensor class will contain three events. One event that gets fired when the temperature of the device reaches or goes above 27 degrees Celsius, which is 80.6 degrees Fahrenheit. This event flags a warning alert. The cooling mechanism is switched on to cool the device back down to an acceptable temperature. We'll create another event that gets fired when the temperature of the device has reached or gone above 27 degrees Celsius and then subsequently falls below 27 degrees Celsius. This event flags an informational alert and the cooling mechanism is switched off. And lastly, we'll create an event that gets fired when the temperature reaches or goes above 75 degrees Celsius, which is 167 degrees Fahrenheit. This event flags an emergency alert. The device is shut down, and emergency services personnel are notified about the event. We discussed in the previous part of this tutorial that an event is raised either by the user's action, for example, the user clicks a button, or the code logic itself. In this example, we are going to use code logic to raise specific events. For more content on advanced C# concepts like this and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. Right, let's get started. Let's create a .NET Core Console app, and let's name this project and solution Thermostat Events app. Let's start by building a custom class to store our event information. Let's name this class Temperature Event Args. And let's make this class inherit from the C# built-in Event Args class. We want our custom class to store the current temperature, so this will be the temperature at the time when an event is raised. And we also want to store the date and time when the event was raised. So let's create an auto-implemented property named temperature and define it as the double data type. Let's create another auto-implemented property named current date time and define it as the date time data type. Next, let's create an interface named iHeatSensor. And we'll include definitions for 3 events in the iHeatSensor interface. All the events are associated with the built-in C# delegate named EventHandler. And here we can pass our custom class, the one we have just created named TemperatureEventArgs, that will be used to store event information, as a generic parameter to the EventHandler delegate. So let's create a definition for an event that will be fired when the temperature reaches or exceeds a predefined emergency level. Let's create a definition for an event that will be fired when the temperature reaches or exceeds a predefined warning level. And lastly, let's define an event that will be fired when the temperature has reached or exceeded the warning level and subsequently falls below the warning level. So next, let's create a HeatSensor class to implement the iHeatSensor interface. And we want to explicitly implement the events defined in our iHeatSensor interface for the HeatSensor class. So one way we can do this is hover our mouse pointers over the red squiggly line under the iHeatSensor text, then select Show Potential Fixes, and then select Implement Interface explicitly. And now you can see Visual Studio has created our event implementations with add and remove accesses. Note that these add and remove accesses are very similar to the get and set accesses that are implemented for C# read-write properties. The add accesses will contain code that is fired when the client code subscribes to the relevant event. The remove accesses will contain code that is fired when a client unsubscribes to the relevant event. So we'll add code to the add and remove accesses in a bit. So one thing I forgot to do was include a method definition for running the heat sensor. Let's include the appropriate method definition in the iHeatSensor interface. And now you can see a red squiggly line under the iHeatSensor text in the class definition for the HeatSensor class. This is because we are not implementing all the members of the iHeatSensor interface. So to fix this, we can hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Implement Interface. And you can see that Visual Studio generates a method implementation for the method that we had not yet implemented for the iHeatSensor interface, the runHeatSensor method. We'll implement code for the runHeatSensor method a bit later. Let's create 2 member variables at the top of the HeatSensor class, both defined as double. The first member variable is named warning level, and the second member variable is named emergency level. These member variables will store values that serve as our triggers for when a relevant event should be raised. For example, if the temperature of the device rises above the emergency level, the appropriate emergency event is raised. So let's set these values within a parameterized constructor. So let's create a member variable named _hasReached warning temperature, and this is defined as the Boolean data type. We'll see the significance of this member variable in a bit. Let's create another member variable which will reference a collection of delegates associated with the events implemented in this class. We could use any of the appropriate collection classes in C# for storing these delegate objects, but we are going to use the built-in C# EventHandler list class for this purpose. So to use the EventHandler list class like this, we must include a directive to the system.componentModel namespace at the top of our code. As mentioned earlier, the EventHandler list class is a member of the system.componentModel namespace. We are going to use the EventHandler list class's addEventHandler method to add the appropriate delegates. The addEventHandler method accepts a key value of type object. For its first argument, this object value serves as a unique key for accessing values in the collection. And its second argument is a value of type delegate. The EventHandler list collection class allows the developer to store delegates that can be accessed within the collection using a unique key. We are also going to implement code using the removeEventHandler method to remove delegate objects from the relevant collection. The method definition for the removeEventHandler method is the same as the method definition for the addEventHandler method definition. Please navigate to this URL for more information on the EventHandler list class. So let's create 3 static read-only objects which will serve as key values that can be used to access the relevant delegates from within the event handler list collection. Let's create another private member variable, which is an array of the double type, named _temperature data. So this array will store mock data to simulate data coming from the heat sensor at regular time periods. So this data will be used to simulate the heat sensor outputting temperature data. So let's create a method named seedData and populate the _temperature data array with data. Note that I'm deliberately including temperature data that is greater in value than 27, which will be used as our warning level. And toward the end, data that is greater in value than the emergency level, which will be set to a value of 75. This is so we can raise our events appropriately when the heat sensor outputs our mock values. Okay, so now let's implement the code for the add and remove accesses for the events that reside in the heat sensor class. So in the add accesses, all we want to do here is add the appropriate delegate to the event list handler collection, which is done at the point where the client code subscribes to the relevant event. So in the remove accesses, all we want to do is remove the appropriate delegate from the event list handler collection, and this is done at the point where the client code unsubscribes to the relevant event. You can see we are using the appropriate key objects when adding the relevant delegate to the collection. We are also able to use the appropriate key to remove the relevant delegate from our event list handler collection. So let's encapsulate functionality for raising the relevant events by creating 3 methods responsible for raising the relevant event for each of the events defined in the heat sensor class. Let's name the first method onTemperature reaches warning level. This method accepts one argument, which is our custom type named temperature event args. The temperature event args class is responsible for storing event data. Let's then write code to reference the relevant event using the _temperature reaches warning level key variable to reference the appropriate delegate within the _list event delegates object, which is derived from the event handler list class. When assigning the value stored in the _list event delegates collection object to the handler variable, we must typecast the delegate to the appropriate delegate type, which is the event handler delegate that accepts the temperature event args type as a generic parameter. Then we need to see if indeed the client code has subscribed to the relevant event. If the client code has subscribed, then the handler variable will not be null. So if the handler variable is not null, we can raise the relevant event by executing the handler delegate object and passing in the appropriate arguments to the handler delegate. The this keyword is the first argument which references the current object, which of course is an object of the heat sensor type. The second argument contains relevant event information and is of the temperature event args custom type. If you'll recall, we made provisions for storing the current temperature as well as the date and time of when the relevant event occurred in the temperature event args class. Right, and we can now repeat the same basic pattern for the other 2 methods responsible for raising the other 2 events declared in the heat sensor class. So let's implement a method to encapsulate raising the temperature falls below warning level event handler event. And let's implement a method to encapsulate raising the temperature reaches emergency level event handler event. And now let's implement a private method named monitorTemperature. This method simulates the heat sensor outputting temperature information for the device being monitored. So this method traverses the data stored in the _temperature data array, which contains our mock temperature data. Let's write code to display the temperature to the console screen each time a temperature is read from the _temperature data array. Then we can create an else-if ladder whereby we can compare the temperature output to the warning level and the emergency level. The emergency level has the highest value that will be evaluated, so this is the first value that will be evaluated. If the temperature is above the emergency level, the emergency event is raised. Else, if the temperature is above the warning level, but below the emergency level, the warning event is raised. Else, if the temperature was above the warning level and subsequently falls below the warning level, we can raise the temperature falls below warning level event. Note how we are using the underscore has reached warning level Boolean member variable to evaluate if the temperature falls below warning level event should be raised. The underscore has reached warning level variable must be set to true when the warning level reached event is raised so that the temperature falls below warning level event can be raised when the temperature subsequently falls below the warning level. When the temperature subsequently falls below the warning level, we must set the underscore has reached warning level variable to false. And for effect, I'm going to introduce a 1-second delay between iterations of the underscore temperature data array. As you can see, I'm using the system.threading.thread.sleep method for this purpose. I'm passing 1000 as an argument to this method. This value denotes 1000 milliseconds, which is 1 second. And let's finish off the heat sensor class by implementing code for the run heat sensor method. So we'll simply write the text heat sensor is running to the screen to indicate that the heat sensor is running. And then let's call the monitor temperature method. Okay, so let's create the interface for the cooling mechanism class. Let's keep this really simple. So this interface contains two method definitions, one named on and the other named off. As the names imply, these methods represent the behaviors of switching the cooling mechanism on and off. Let's create a class named cooling mechanism and implement the iCooling mechanism interface. And each method will simply write appropriate text to the screen. Let's create an interface named iDevice. This interface contains two method definitions, one named runDevice, the other named handleEmergency. We'll create the class that implements the iDevice interface in a bit, but let's first create a class to represent the thermostat. Let's first create an interface named iThermostat. This interface contains one method definition named runThermostat. Right, let's create a class named thermostat that implements the runThermostat method. Let's create a member variable of type iCooling mechanism. Let's create a member variable of type iHeatSensor, and let's create a member variable of type iDevice. Let's create two constants, one to store the warning temperature level, which is set to 27 degrees Celsius, and one to store the emergency temperature level, which is set to 75 degrees Celsius. Please note that these figures are arbitrary and serve only to help us with the code example. Let's create a parameterized constructor that accepts an argument of the iCooling mechanism type, an argument of the iHeatSensor type, and the iDevice type. We want the thermostat to have a reference to the device to which it is attached. Let's set the appropriate member variables to their counterpart arguments within the constructor. Let's create a method where we'll wire up the events contained in the heat sensor class. Let's name this method wireUpEvents to event handlers. So let's use the heat sensor object passed into the thermostat class to wire up all of the appropriate events. So to do this, we can write _heatSensor dot the event name, which is in this case temperature reaches warning level event handler, then followed by the plus equals operator. Then we are able to press the tab key to auto-generate an appropriate method definition. Then we can rename the method if we choose and click the apply button to confirm the change. So let's write code to wire up the remaining events. So in the run thermostat method, let's add code to write that the thermostat is running. Let's call the wire up events to event handler's private method. And lastly, let's call the run heat sensor method on the underscore heat sensor object. Let's write code for each of the client event handlers. So to handle the event, for when the temperature reaches or exceeds the warning level, let's first change the color of the font to dark yellow. Let's write warning alert. The warning level is between warning level and emergency level to the console screen. Let's then write code to switch on the cooling mechanism. Then when the temperature subsequently falls below the warning level, we want the font to change to a blue color. And let's write information alert, temperature falls below warning level is between warning level and emergency level. And then to handle the emergency event, let's change the font to a red color. Let's output emergency alert, emergency level is emergency level and above. And this event is handled slightly differently to the other event handlers because we are calling the underscore device object's handle emergency method. We are using the iDevice interface to handle the emergency event in the device object's code, which we'll soon implement. And we must make sure that each font color is reset after each event is handled. Okay, so now let's create a class to represent our device, i.e. the device that we are monitoring for temperature changes. Let's name it device, and within the class's definition, let's indicate that we wish to implement the iDevice interface. Let's hover our mouse pointers over the red squiggly line, under the iDevice text, click Show Potential Fixes, and then click Implement Interface. And Visual Studio auto-generates implementations for the members of the iDevice interface for us. So let's implement code for the handle emergency method. And we'll simply write out a basic narrative of what should happen in the event of an emergency. So let's write sending out notifications to emergency services personnel to the console screen. And then in the event of an emergency, we also want to shut down the device. So let's create a private method named shutDownDevice. And this method simply outputs a narrative stating that the device is shutting down. Let's call the shutDownDevice private method from the handle emergency method. Let's implement code for the runDevice method. So let's simply output that the device is running to the console screen. Then we want to construct our objects for our cooling mechanism, heat sensor, and thermostat components. And we'll use their interface abstractions to define each of their types. And I've encountered a bit of a snag here when writing the code to construct the heat sensor object. We have already created the constants for the warning level and emergency levels in the thermostat class. I think these constants should rather be members of the device class and passed into the heat sensor class during the construction of the heat sensor object. So let's create the two relevant constants in the device class. And so that we can encapsulate the values of these constants and expose the values of these constants publicly, let's create two corresponding read-only properties. Let's first create definitions for these read-only properties in the iDevice interface. And then let's implement the code for these properties in the device class. And then within the thermostat class, which has a reference to the relevant device object, we can replace the references to the relevant constants that once resided in the thermostat class with references to the relevant read-only properties of the device object. Okay, let's then write the code to run the device from our main method. So let's write code to prompt the user to press any key to run the device. Then let's instantiate an object for the device. Then let's call the relevant object's runDevice method. Sorry, I know I'm jumping around here a bit. We still need to finish off the code for the runDevice method. Let's finish creating the thermostat object. Then let's call the object's runThermostat method. let's run the code. And you can see by the status output the device is running, the thermostat is running, and the heat sensor is running. The temperature changes of the device can be seen with the output of each temperature to the console screen. A warning event is raised when the temperature exceeds 27 degrees Celsius. The cooling mechanism is then switched on. But there's an issue because when the temperature subsequently falls below 27 degrees Celsius, the relevant status is not being outputted to the screen. Instead, the code is raising the warning event. So let's investigate what is going on here. And the issue was caused, I think, because of all the copying and pasting. I forgot to change the call to the on temperature reaches warning level method to a call to the on temperature falls below warning level method. Obviously, a call to the on temperature reaches warning level method is inappropriate for the condition when the temperature has reached or is over the warning level and then subsequently falls below the warning level. So let's fix this issue and let's run the code. And that is a correct result. We can see the cooling mechanism is turned on when the temperature of the device exceeds the warning level. And when the temperature has been above the warning level and subsequently falls below the warning level, the correct event is raised. The correct status is therefore outputted to the screen in a blue font. And then the cooling mechanism is switched off. And we can see that all the events are firing correctly and being handled correctly. Toward the end, the emergency event is being handled correctly, which is in line with the mock temperature data that we created for this example. Great! I hope you have enjoyed this video on handling multiple events within a class, using the add and remove accessors. We also used the event handler list built-in C# collection class to add and remove the relevant delegates for when a user subscribes or unsubscribes to an event. Hi, and welcome to the third part of this tutorial on C# events. We have discussed that events can be triggered either by code logic or through a user's actions, for example, clicking a button. In the previous parts of this tutorial, we focused on events triggered by code logic. In this video, we'll focus on events triggered through user actions. So, in most of the tutorials provided by this channel regarding C#, the .NET Core Console App project template has been used as a starting point for creating the relevant sample code. This has been done deliberately so that we can focus on the language of C# and not be distracted by framework-related concepts. In this video, we'll do something a little bit different. We'll create a very basic code example, and we'll use the blank app Universal Windows project template to create the project responsible for the front-end functionality of our application. So we are going to develop a basic application using the UWP, or Universal Windows Platform Framework. This is so that we can look at how user actions, for example, a button click, can trigger events and how the relevant events can be handled appropriately in code. In this video, we'll show how a separation of concerns can be achieved whereby the front-end display functionality is loosely coupled with the back-end functionality. Specifically, we'll look at how events can be implemented to achieve this. So, one of the advantages that can be achieved by separating concerns is we can have one team that specializes in front-end design, working on the look and feel of the application, and the back-end functionality can be developed by a completely different team. These two concerns can evolve independently from one another and in parallel to one another. The integration of the relevant components at an appropriate time can become a relatively trivial task. We are going to show how this loose coupling effect is achieved through the appropriate use of an event. A design pattern that can be used to achieve this loose coupling of front-end and back-end components is called MVVM, which stands for Model View View Model. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you can be notified of future content released from this channel. Another advantage of implementing the MVVM design pattern to achieve this loose coupling of components is we are able to easily port, for example, the back-end functionality to other platforms. Let's say, for example, you have a particular app which is being distributed via the Microsoft Store. This app was written using the UWP framework. Let's say the app is selling really well. Marketing research tells us that there is a huge demand for this app to run on iOS and Android platforms. Time is a key factor in keeping the momentum of sales going for this application. So we want this app to be appropriated for iOS and Android platforms as soon as possible so that the app can be distributed via Apple's App Store for the iOS implementation of the app, as well as Google Play for the Android implementation of the app. So we know that we can use the Xamarin technology to create a cross-platform app for iOS and Android devices. So if we have designed our app appropriately using the MVVM design pattern, the back-end functionality that we have already created would not need to be recreated for the iOS and Android platforms. Please navigate to this URL for more information on Xamarin. A team specializing in Android and iOS front-end design could focus on the native front-end functionality for their respective platforms. Or the use of Xamarin Forms could also be utilized for the creation of the front-end design using XAML. We'll discuss XAML in a bit. The back-end code already created for the UWP version of the app can be reused for the Android and iOS apps created using the Xamarin technology. For more information on Xamarin Forms, please navigate to this URL. The appropriate use of the MVVM design pattern could make the integration of the front-end functionality with the back-end functionality a relatively trivial task. The details of MVVM are beyond the scope of this tutorial. Please navigate to this URL for more detailed information about MVVM. Model View View Model. UWP stands for Universal Windows Platform. So a UWP application can run on any Windows device that runs Windows 10 or Windows versions greater than version 10. Windows 11 is due to be released on July the 29th, 2020. These devices can include PC, tablet, Xbox, HoloLens, Surface Hub, and Internet of Things devices. So we are not going to go into depth regarding the Universal Windows Platform. UWP demands an entire course on its own. If you want to learn more about Universal Windows Platform, please navigate to this URL. But let's look at a very basic example of loosely coupling back-end functionality from front-end functionality using events on the Universal Windows Platform. So let's create a project based on the blank app Universal Windows project template. Let's name this project and solution Employee UWP App. So once we click the Create button, we are prompted with a dialog box where we are able to choose the minimum version and target version that our UWP application will support. So to aid us with our decision, let's click on the link labeled Which version should I choose?, which is available in the bottom left-hand corner of the relevant dialog box. So we are presented with a web page, And at the end of the first paragraph on the web page, it states, projects using .NET Standard 2.0 must have a minimum version of build 16299 or later. So we are going to develop our backend functionality using .NET Standard 2.0. So let's choose version 16299 from the drop-down list labeled minimum version. Right, let's add a standard library project to our solution. And let's name it Employee Component. This library will contain our backend functionality. So firstly, let's reference our Employee Component project from our UWP project. So let's right-click the References node within our UWP project and add a reference to the Employee Component project. Okay, let's delete the class that has automatically been generated. Let's create a class that will serve as our view model, and let's name this class Employee View Model. As the name suggests, a view model represents the data that will be displayed to the user. Let's make this class a public class. Let's write code so this class implements the iNotifyPropertyChanged interface. We must include a directive to the system.componentModel namespace. The iNotifyPropertyChanged interface is a member of the system.componentModel namespace. So to do this, we can hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Using System.componentModel. This interface contains an event that is key to how we can achieve a loose coupling between the backend component and the UWP front-end component that we'll soon develop. So, to implement the iNotifyPropertyChanged interface, let's hover our mouse pointers over the iNotifyPropertyChanged text, which has a red squiggly line under it, and click Show Potential Fixes, and then let's click Implement Interface. Note that a public event named PropertyChanged, which is defined as the delegate type PropertyChanged event handler, is generated for us. This event will be raised to the front-end code when a relevant property value in this class is changed. This example is going to be simplistic so that we can focus on the core concepts of this video, namely how events can be used to achieve a loose coupling between front-end and back-end components. So let's create a read-write property named firstName, and let's create a private member variable named _firstName. Let's encapsulate the _firstName private member variable within the firstName property. And within the set accessor of the firstName property, let's include code to raise the PropertyChanged event. So if the firstName property is changed, we want to raise the PropertyChanged event, which will have the effect of notifying the front-end view presented to the user that the relevant field must be changed on the front-end display, so that the change in value of the property is presented to the user. And this is a key concept to understand. When the view model is changed, the event notifies the actual view presented to the user of the change, and the change is then reflected in the view presented to the user. So the view presented to the user is never directly changed, for example by referencing an element of the view presented to the user. The underlying view model, which is part of the back-end code, is changed, and this change is propagated to the view presented to the user through the implementation of the PropertyChanged event. We'll demonstrate later on how the UWP front-end component subscribes to the PropertyChanged event to receive notifications when a relevant property value changes. Let's wrap the relevant functionality that raises the PropertyChanged event in a private method, and let's name this method NotifyPropertyChanged. Notice that this method accepts a string argument which will contain the name of the property that is changed. So now, within the set accessor of the first name property, let's write code to call the notify property changed private method for when the first name property is changed. And let's create auto-implemented properties for the other employee fields: ID, last name, annual salary, gender, and is manager. Let's create a class named employees. We are going to be storing the employee view model objects in a generic collection type called an observable collection. The observable collection type represents a dynamic data collection that provides notifications when items get added, removed, or when the whole list is refreshed. For more information about the observable collection class, please navigate to this URL. So firstly, let's include a directive to the system.collections.object model namespace. The generic observable collection class is a member of this namespace. This class will simply contain a method that returns a collection of employee records. Let's create a public method named getEmployees. We want this method to return a collection of employee data. So the getEmployees method returns an object of type observable collection. The observable collection is a generic collection type, and we are able to strongly type the collection with the employee view model type. So let's include code within this method that creates a new observable collection object and assign the relevant object reference to a variable named employees. Let's write code to return the employees object. And I've made up some employee data for our employee view model objects that we can add to the observable collection object we have named employees. So to save time, let's navigate to a GitHub repository where I have already uploaded the code for this tutorial. So please navigate to this URL. Let's select the relevant code that adds the employee data to the employees observable collection and appropriately paste it into our code editors. We could have written code to retrieve this data from a data source, like for example a SQL Server database, but in the interests of keeping this code sample simple, we are using mock data as a substitute. The observable collection object represents a dynamic data collection that provides notifications when items get added, removed, or when the whole list is refreshed. We are going to use our observable collection type, which is strongly typed to store objects of type employee view model, to bind our collection of employee view model objects to a list view that we'll create in our front-end design when we develop the UWP component. Okay, so let's develop our UWP component. So the user interface for a UWP application is created using a declarative markup language named XAML, which stands for Extensible Application Markup Language. We are not going to go into the details of XAML in this tutorial, but here's a basic explanation of what XAML is. In a UWP application, XAML is used to define UI elements, data bindings, events, and other features. XAML elements map directly to Common Language Runtime object instances, while XAML attributes map to Common Language Runtime properties and events on those objects. For more information on XAML, please navigate to the following URL. So as mentioned earlier, I have already uploaded the relevant code sample to GitHub. In the interests of time, let's copy the relevant XAML from GitHub, and then we'll paste the XAML code over the XAML currently in the mainpage.xaml file. Right, so let's navigate to this URL. Let's copy all the XAML code from this page to our clipboards. And let's paste the XAML code in our clipboards over the XAML code currently in our mainpage.xaml file. And if we look at the XAML code, here you can see a blue squiggly line under the code where we are binding a list view data template element to the employee view model type. The reason for the blue squiggly line is because we need to compile the employee component so that our UWP project is referencing the relevant latest compiled assembly. So let's compile the employee component. and the blue squiggly line goes away. Great. And we can also see a design view rendering of our XAML code. If we take another look at the XAML code, you can see that the data binding functionality in the first name field includes a mode attribute which is set to the value of one way. This is an important part of the functionality that allows changes to the first name property of our employee view model objects to be reflected in the relevant list view displayed to the user. So in our code example here, we are demonstrating one-way binding from the view model to the list view element of the view. Let's write the code in the code behind file named mainpage.xaml.cs. The code we are going to write here will enable the user to select an employee record from the list view that is created through the XAML code, which will contain a collection of employee records. The user will then be able to dynamically change the first name field for the selected employee record by typing the new first name value into a text box and clicking a button to confirm the change. Let's create a member variable named _employeesOC, which is of the observable collection generic collection type and is strongly typed with the employee view model type. Let's create a public field named changeFirstNameCommand. This is a public field and is defined as the XAML UI command type. For more information on the XAML UI command type, please navigate to this URL. Let's write the code in the constructor of the main page class. Let's create a new object of type employees. So let's take a quick look at the XAML code. And you can see here, we have a list view named employee list. And you can see that there is data binding markup to bind the fields in the list view named employee list to each of the fields defined in our employee view model type. So let's go back to the mainpage.xaml.cs class. And let's write code to bind the data stored in the _employeesOC observable collection object to the employee list view. Note that the item source property in the employee list view is set to the _employeesOC observable collection. So let's go back to the XAML code. Notice here we have a button named btn change first name that contains an attribute named command. And this code is binding the btn change first name button to the public field named change first name command that we defined as the XAML UI command type in the main page class. Also notice that the command parameter attribute includes code that binds to the employee list view element. So let's go back to the mainpage.xaml.cs class and let's create a new XAML UI command object for the change first name command public field. And let's use the += operator to subscribe to the execute request event on the change first name command XAML UI command object. So after we have typed the += operator, we can press the tab key and a method with the appropriate method signature is generated for us. So when the user clicks the button named btn change first name, the code in this method will be invoked. So let's write the code for this method. Firstly, let's write code to get a reference to the employee list view object. We can use the args.parameter property to get a reference to this object. We must typecast this object to the list view type. Then let's write code to check if an item in the list view has been selected. If an item has not been selected, the selected index property will be -1. So if this selected index property is not -1, we can use the relevant list view object's selected index property to index the underlying observable collection object. And we want to set the relevant item's employee first name field to whatever the user types in the relevant text box. If we look at the relevant XAML markup code, we can see that a text box element is included in our markup. This text box can be used to rename a selected employee's first name field to whatever the user types in the relevant text box. So let's run the code. So the employee list view is not populating. Let's investigate why this is occurring. Okay, so we haven't included the code to assign the relevant observable collection object named _employee_OC with a value returned by the employees class's getEmployees method. The getEmployees method populates the observable collection object with objects of the employee view model type and returns the relevant observable collection object to the calling code. So to fix the issue, let's write the code to assign the _employee_OC variable with a value returned by the employees.getEmployees method. Let's run the code again. Great! That has resolved the issue. We can see that our list view is populated with employee view model data. Okay, so let's select the third record, and in the text box here, let's type Bob, and then press the button that is wired up to our change first name command object. And let's repeat the same process for some of the other employee records. Great! We are now able to change the employee record's first name field on the front-end display by updating the underlying observable collection. Note that the code is not updating the employee list view object directly. When the relevant underlying observable collection is changed, an event notifies the employee list view object of this change, and the relevant changes are reflected on the front-end display. If we look at the change first name command _execute request method that gets invoked when the btn change first name button is clicked, we can see that the underlying observable collection object is changed and the employee list object is not directly changed. This highlights the decoupling of the UWP front-end component from the employee component, which is responsible for data handling and business rules. For example, when the first name field was changed for the third employee record, the property changed event, which is a member of the iNotifyChanged property interface, was fired, signaling to the front end that there has been a change to the first name field in the relevant employee view model object, which must be reflected in the relevant list view front-end object. And just for fun, let's include code to make our application speak to the user. So I've already prepared the code that will make our application talk to us in the relevant GitHub repository. So let's navigate to this URL. Let's copy the speak async method to our clipboards and paste it into the mainpage.xaml.cs file. This method includes an asynchronous method call to the synthesized text to stream async method. In order to call the speak async method that we have just included within our code, we must appropriately include the async and await keywords. I'm also going to make a minor change in that I'm going to rename the _employee_OC variable to _employees_OC so that the code we have just created is consistent with the code in the relevant GitHub repository. Let's run the code.
Changing first name from Bill to Bob. Changing first name from Jamie to Don. Changing first name from Sally to Debbie.
Excellent. So to summarize, This code that we have just created shows how the iNotify_changed interface and the generic observable collection can be implemented to loosely couple the front-end component from the relevant code within the back-end component. This loose coupling effect has many advantages, which can include reuse of components across disparate platforms. For example, let's say we have an initial application written to run on multiple Windows devices through the use of the appropriate UWP project template, and then at a later stage, we decide that we want this application to run on iOS and Android platforms. The component responsible for the implementation of business rules and data handling written using the standard library project template can be easily ported to run on the Android and iOS platforms without the need to change the relevant code. We do not need to rewrite this code for the Android and iOS platforms. Separation of concerns allows separate teams to work independently from one another. For example, the front-end XAML experts, or as the case may be, the Android and iOS front-end developers, could focus on the look and feel of the application and the user experience of the application, while not having to worry about the details of the business rules and the database handling functionality. A separate team that specializes in writing the business rules and database-related functionality can focus on this concern without worrying about the implementation detail of the front-end design. The front-end and back-end functionality can evolve independently from one another and in parallel to one another. The front-end and back-end components can then be seamlessly integrated with one another at an appropriate time. I hope you have enjoyed this tutorial on events raised through user actions in the context of a UWP application. UWP is a very powerful platform that can be used for creating rich user interfaces that can run on multiple Windows devices. Examples of related Windows-specific frameworks include WPF, or Windows Presentation Foundation, and WinForms. If you want to learn more about WPF, please navigate to this URL. And if you want to learn more about WinForms, please navigate to this URL. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of new releases from this channel. If you feel you have gained value from viewing this video, please hit the like button and please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. As always, the code created in this video can be downloaded from GitHub. A link to the relevant repository has been included below in the description.
Thank you, and take care.
Hi and welcome to the fourth part of this tutorial on C# events. This video is also part of a tutorial that serves as the fourth part of an advanced C# course. In this video, we'll focus on the observer design pattern. This is a very powerful design pattern and is suitable for any scenario that requires push-based notifications. The implementation of the observer design pattern entails subscribers registering to receive notifications from a provider. Push notifications simply means that the notifications are pushed from a central point to the relevant subscribers. The source of the push notifications is known as the provider, also known as the observable. Observers register with the provider, in other words, subscribe to the provider, and whenever a predefined condition, event, or state change occurs, one of the observer's methods is called by the provider. In this method call, the provider can also provide current state information to observers. So note that the observable can also be referred to as the provider, and observers can also be referred to as subscribers. So I'll be using these terms interchangeably throughout this tutorial. For more content like this on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. In .NET, the implementation of the observer design pattern can be achieved when the subscribers class or observers implement the generic system.iObserver generic interface and the provider class implements the system.observable generic interface. The generic type represented here with the capital T represents the type, which can be a user-defined type, that encapsulates the notification information communicated from the provider to its subscribers through push notifications. So the generic type, represented by the capital letter T in the interface definitions of both the provider class and the subscriber classes, is key to how loose coupling between provider and subscribers can be facilitated while still enabling rich and extensible data to be pushed from providers to subscribers. The System.iObservable and System.iObserver built-in .NET generic interfaces enable this pattern to be reused for multiple scenarios. The generic type represented by the capital T allows for user-defined types to serve as communication vehicles that can be extended without breaking the design of the relevant application. So let's look at a quasi-real-world example that can be used to explain the observer design pattern and give us an idea of when it is appropriate to use this design pattern. So we'll have to use our imaginations a bit to picture this example. Let's say a particular company owns a building with an automated security system. One of the functions of this security system is to identify external visitors arriving at the building, for example, to have a business meeting with one of the employees that work inside the building. So the process first involves the external visitor registering to visit the relevant employee on a particular day. Let's say that before an external visitor arrives at the building for the relevant visit, the external visitor must first register and during the registration process provide a clear photograph of the external visitor's face as part of the registration process. So when the external visitor arrives on the day of the visit and attempts to enter the building, a camera first scans the external visitor's face and subsequently sends the relevant pictorial facial information to a system whereby biometric artificial intelligence algorithms are applied to ascertain whether this particular visit can be authenticated, i.e., has this person registered, and if so, can this person be verified as the person claims to be? So this is essentially an automated authentication process. Once the relevant visitor has been identified, the visitor is automatically given access to the building. This triggers notifications to be sent to the building's security team and any internal staff members, i.e. employees of the company that owns the relevant building, who have subscribed to receive notifications regarding the relevant actions of the external visitors. The information that is sent to the subscribers, i.e. the notification data sent from the provider, contains information about the relevant external visitor and the time the relevant external visitor gained access to the building, and then subsequently, once the visit is completed, a notification is sent when the external visitor exits the building. Another notification will be sent to all subscribers from the provider when a predefined time is reached and all external visitors have exited the building. For example, the predefined time could be 6 p.m., which has been deemed the end of the working day for the relevant company. The rule could be that after this time, no external visitors can gain access to the relevant building. In this example, we'll refer to this time as the cutoff time. Okay, so as I've said, we need to use our imaginations a bit here because we are going to implement code for the scenario just described within a console app.NET Core framework. In other words, the code will be highly simplified so that we can focus on understanding the observer design pattern. So the provider in this example will be the security surveillance system used to identify external visitors that have registered to visit a member of staff within the relevant building on a particular day. This example will contain two types of subscribers. One of the types of subscribers that we will create will represent the security team. They must be notified of all significant movements of external visitors, for example, entering and exiting the building. The other type of subscriber will represent any individual internal staff member who has subscribed to receive relevant notifications regarding external visitors. This employee would subscribe because a visitor must have a point of contact inside the building in order to successfully register as an external visitor. When the external visitor is authenticated on the day of the visit, a notification will be sent to the security team as well as any employee who is registered as the point of contact for the relevant external visitor. Okay, let's look at an overview of the main classes that will be created for this example. So here is a class that represents the observable. This class will represent a central place where surveillance data is processed. We'll create two classes that represent two types of observer. The first class represents an employee, i.e. a person that works inside the relevant building, who wants to be notified when a particular external visitor enters the building. This class is named Employee Notify. The second class represents the security team, who must be notified when any external visitor enters or exits the relevant building. This class is named Security Notify. We have a class here named External Visitor, which represents an outside visitor to the relevant building. This class serves as the generic type argument to both the iObservable generic interface implemented by the observable class, as well as the generic argument to the iObserver generic interface, which is implemented by the observer classes. So this class allows data about the external visitor to be communicated from the observable object to its observer objects when the relevant notifications are sent. We have an iEmployee interface and an employee class that implements the iEmployee interface. The employee class provides a way to store details about an employee who works inside the relevant building. This class represents the employee details of a person who serves as a point of contact for an external visitor. An employee object is passed into the constructor of the Employee Notify class during the instantiation of an object derived from the Employee Notify class. So in summary, here are our main classes: Employee Notify, an observer class; Security Notify, an observer class; Security Surveillance Hub, the observable class; iEmployee, an interface defining an internal staff member record; Employee, a class that implements the iEmployee interface, so it represents an employee record; External Visitor, a class representing the person that has registered to visit a member of staff that works inside the relevant building. This class represents a person that must be authenticated on the day of the relevant visit. Let's look at the class that will serve as our observable class. We'll name this class Security Surveillance Hub. This class represents a central location where surveillance system information is processed and will be responsible for notifying subscribers with the relevant information about an external visitor. So notifications will be sent to the relevant observers when an external visitor enters the building, and another notification will be sent to the relevant observers when an external visitor exits the building. Firstly, let's answer the question, how can we implement a class so that it can be instantiated as an observable object? The answer to that question is that a class that will be instantiated as an observable object must implement the iObservable generic interface. The iObservable generic interface is a built-in .NET interface that is a member of the system namespace. The next question is what makes the observable interface a generic interface? The iObservable interface is generic because the calling code is able to pass a type as a generic argument to a class that implements the iObservable generic interface. In our example, the type that we'll pass as the relevant generic type argument will be a user-defined type named External Visitor. As you may have guessed, this class will represent an external visitor. We'll discuss the External Visitor class in more detail a bit later. The iObservable generic interface contains one method definition. This method definition is for a method named subscribe. The subscribe method contains one parameter of a type that implements the iObserver generic interface. So this parameter is defined as an observer type. We'll discuss the iObserver generic interface a little bit later. So the subscribe method must be implemented by the type that implements the iObservable generic interface. The implementation of the subscribe method must contain functionality that is executed when an observer subscribes to receive notifications from the relevant observable object. So we've now looked at the essence of what we are trying to achieve here by implementing the observer design pattern. Let's get started and create the code example. Let's create a project based on the console app.NET Core project template. Let's name this project and solution Building Surveillance System Application. So for our first class, let's create a class that represents the external visitor. This class represents the information about an external visitor that will be sent to the relevant subscribers when an external visitor enters the building and subsequently exits the building once the external visitor completes the external visitor's visit. So let's create a public class and name it external visitor. Let's create the properties for the external visitor class. So let's create a property for ID defined as int, first name defined as string, last name defined as string, company name defined as string, job title defined as string, entry date time defined as date time. This property will store the date and time of when the relevant external visitor entered the building. Exit date time defined as date time. This property will store the date and time of when the relevant external visitor exited the building. And lastly, an auto-implemented property named employee contact ID, and let's define this property as int. This property facilitates the storage of the ID of the internal employee, i.e. an employee who works within the building, responsible for being the point of contact for an external visitor on the relevant day of the external visitor's visit. Great, and that is our external visitor class. So let's create our observable class. Let's create a public class named Security Surveillance Hub. As explained earlier, this class serves as a metaphor for a central location where security-related information is processed. So, for example, an external visitor's face is scanned before gaining access to the building, and this pictorial information is subsequently sent to the Security Surveillance Hub, where the biometric information in the relevant image is compared against registered image information captured when the external visitor registered to visit the building. So if the two pieces of information match, the visitor is granted access to the building, which will trigger notification information about the external visitor to be sent to the relevant observers. So as discussed earlier, in order for this class to represent our observable, it must implement the iObservable generic interface. So let's write the code to do this, and let's pass in the external visitor type as our generic type argument. What makes the iObservable interface a generic interface? It is a generic interface because we are able to strongly type the iObservable interface. The capital T within less than and greater than symbols in the iObservable interface definition means that we are able to replace the T with our C# type. When this is done, it means we have strongly typed our generic interface. So let's strongly type the iObservable interface with our external visitor class like this. Generics allows us to stipulate a particular type for the relevant type placeholder at compile time. Note that a capital T is commonly used to represent the generic type placeholder. Generic functionality can also be accomplished through the use of the .NET System.Object type. As we know, all types in C# ultimately inherit from the System.Object type. So we are able to typecast a variable at runtime to any managed .NET type. The advantage of using generics for the same purpose is that we can achieve the same functionality, but this is done at compile time. This provides the advantage of compile time type checks, ensuring type safety, as well as results in greater performance for our code because we are able to omit the need for runtime typecasting. Typecasting, which is performed at runtime, also carries the risk of incurring runtime errors. Please don't worry if you didn't understand this brief explanation of why generics is significant Generics will be discussed in detail in upcoming tutorials. So let's develop the Security Surveillance Hub class. So you can see that there is a red squiggly line under the iObservable text in the class definition. This is the C# compiler letting us know that we have not yet implemented code for the member definitions of the iObservable generic interface in the Security Surveillance Hub class. So let's hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and click Implement Interface. As you can see, there is only one method definition in the iObservable interface that we must implement in the Security Surveillance Hub class. This method is named subscribe. Notice how the subscribe method definition contains a parameter of type iObserver, and the iObserver parameter type definition is automatically strongly typed with the type definition with which we have already strongly typed the iObservable interface. So we have strongly typed the iObservable interface with the external visitor type, and this has propagated to the subscribe method definition when we automatically generated the method definition that is contained in the iObservable generic interface, i.e. the subscribe method definition. This is a key concept to understand when understanding how we are able to use the iObservable and iObserver generic interfaces to implement the observer design pattern. The generic type gives us a means for creating a loose coupling between the observable component and the relevant observer components. The generic type, both defined in the iObservable and iObserver interfaces, allows the developer to strongly type these two interfaces with a common type. In this example, we are strongly typing these two interfaces with the external visitor user-defined type. This will become clearer as we develop this example application. Right, let's implement the code for the Security Surveillance Hub class. So let's create two member variables. Both of these member variables are of the generic list type. Let's define the first one and name it _external visitors. As the name suggests, this list will store a list of external visitors. When an external visitor gains access to the building, the external visitor is added to the _external visitors list. And you can see that we are strongly typing the _external visitors list with the external visitor user-defined type. Let's include a directive to the system.collections.generic namespace. The second generic list we need to define will store a list of observers. So this list will contain objects that are derived from the iObserver generic type that is strongly typed with the external visitor user-defined type. Let's name this generic list variable _observers. So when an observer subscribes to receive notifications from the observable, the relevant observer is added to the _observers list. Conversely, if an observer unsubscribes, the relevant observer is removed from the _observers list. So the subscribe method will be the last method that we will implement. As discussed, the subscribe method has to be implemented because it is a member of the iObservable generic interface, which the Security Surveillance Hub class implements. For now, let's create a public method that gets called when an external visitor gains access to the building. Let's name this method confirm external visitor enters building. This method's parameters contains relevant information associated with an external visitor, namely ID defined as int, first name defined as string, last name defined as string, company name defined as string, job title defined as string, entry date time defined as date time, and employee contact ID defined as int. Then we can write the functionality to instantiate an external visitor object and set the properties of the object we have derived from the external visitor user-defined type with the values that will be passed as arguments to the confirm external visitor enters building method. Then let's write the code to add the newly created external visitor object to the _external visitors list. As mentioned, the _observers list is populated with observers. Observers are, of course, objects that have subscribed to be notified when certain conditions are met, for example, an external visitor entering the building. So this method represents an external visitor entering the building. The visitor has been authenticated and is automatically given access to the building. So let's use our imaginations, and let's say that when an external visitor enters the building, the framework in which our observable exists invokes the confirm external visitor enters building method. The observable can now notify all subscribers of this event, as well as send the relevant data pertaining to the event to all the relevant subscribers. In this particular example, the relevant data is encapsulated with the external visitor object, which is derived from the external visitor class. Remember, the iObserver generic interface is strongly typed with the external visitor user-defined type, which makes it easy to send the data to the relevant observer objects. The relevant observer objects are stored within the _observers list. So in order to notify the relevant observers with the relevant data, we can write code to traverse the _observers list and call each observer object's onNext method. Note that when we call each observer object's onNext method, we are passing the relevant external visitor object as an argument to the onNext method. This is how each observer receives notification data whenever the relevant event occurs. In this example, the relevant event is an external visitor gaining access to the relevant building. So how does the observable, i.e. an object derived from the current class we are creating, know that an observer object implements a method named onNext? And even further to that, how does the relevant observable object know that the onNext method accepts an argument of type external visitor? This is at the heart of how the observer pattern works in C#. Each observer object is derived from a class that implements the iObserver generic interface. If we look at the definition for the iObserver interface, we see three method definitions, namely onNext, onError, and onCompleted. The onNext method contains a parameter of a generic type. So when we create an observer class a bit later, we'll strongly type the iObserver interface that our class must implement with the external visitor user-defined type. This action will mean that the onNext method will be strongly typed with the external visitor user-defined type. So the external visitor type becomes a common communication facility between the observable and the relevant observers. So the fact that we know that each observer implements the iObserver generic interface means we know that each observer object implements a method named onNext. The fact that the iObserver interface for each observer class is strongly typed with the external visitor user-defined type means that we know the type of the argument that needs to be passed into the onNext method. The iObserver generic interface contains a definition for a method named onError. This allows for the observable to notify relevant observer objects if an exception occurs, and also provides information about the exception through the built-in exception type. We are not going to implement custom functionality for the onError method in this example. Each observer object must, however, implement code for the onError method because the definition for the method is contained within the iObserver generic interface. The last method that we need to talk about is the onCompleted method. So we will be implementing custom code for the onCompleted method in this example. The onCompleted method does not contain any parameters. The onCompleted method notifies the observers that the observable has finished sending notifications. So this method should be called for each observer when a condition is met, whereby no more notifications need to be sent to the relevant observer objects. In this example, the onCompleted method will be called on all observer objects within the _observers list when the relevant cutoff time has been reached on a particular day and all external visitors have exited the building. The cutoff time could be, for example, designated as 6 p.m. There may be external visitors who exceed this time constraint due to, for example, a meeting that goes on for longer than expected, or something of that nature. So two conditions need to be met for the onCompleted method to be invoked. A certain time in the day is reached, for example 6 p.m., and all external visitors have exited the building. So next, let's implement a method that is called when an external visitor exits the building. So let's name this method confirm external visitor exits building. This method is a public method that contains two parameters. One parameter